Much. So today I'm going to shift gears a little bit now and tell you about gamma delta T cells and how we're using this really incredible and powerful cell type to really change how we think about cell therapy and oncology. And to do that, I'm actually going to try and tell you a little bit of a story. And the story actually starts 30 years ago. And this was when our chief scientific officer, Dr. Larry Lamb, was actually a pediatric transplant nurse. And at the time, they were doing something called salvage transplants, which today we call haploidentical stem cell transplants. And what that means is that these kids that they were transplanting didn't have good donors. And this was a last-ditch effort to try to give them some sort of transplant to expand their life. And what you're actually looking at here is a wreath from one of these 6-year-old patients during one fall when he treated six 6-year-old girls. And unfortunately, he came in, and the fourth girl, the one who had actually made this wreath, had just passed away. And he actually found himself crying in the hallway because he couldn't understand, of the 4 girls that passed and the 2 girls that lived, what was the difference. On paper, they all looked the same. Their donor profiles looked the same. Their profiles as recipients looked the same. And it took him on a 30-year odyssey that's culminated in IN8bio, where he found the gamma delta T cell. And I'm going to tell you today, one, how we're taking this observation from 30 years ago and actually turning it into a therapy, but why we believe that the gamma delta T cell is so powerful in doing what it does. And those 2 girls who remained in remission are actually still alive today. So we've gotten to our IN8bio cell therapy thesis, and we think that we need to think about cell therapy a little bit differently as we advance our knowledge of the immune system and our understanding of rare immune cell types. The first is durability. How do we actually take cell therapy and achieve durable responses? The problem is we sort of found the needle in the haystack first with something like CD19. And the reality is CD19, while it can be curative, it uses cell therapy a little bit more like a sledgehammer and less like a scalpel, where it just eliminates the entire B cell compartment. So instead of using monotherapy after monotherapy until failure, how do we synergize with chemotherapies? How do we synergize with transplant and cell therapy? How do we synergize with bispecifics and cell therapies to actually drive durable responses in the upfront settings? And so I'm going to talk about that. How do we start using cell therapy like a scalpel to achieve tolerability, where we can actually eliminate the tumor cells but preserve the healthy tissue? And then finally, how do we conquer tumor heterogeneity, where we can't just obliterate your heart, your liver, or your lungs because you have a tumor? We need to cover the entire heterogeneity of the tumor, but leave the healthy tissue alone. And this is our pipeline today. And to follow the line of this story, what I'm going to focus on is INB100, which is our phase 1 program that's actually in haploidentical transplant in adults with complex leukemias. And so what is a gamma delta T cell, which was actually the first question that Dr. Lamb himself asked when he identified it out of his retrospective analysis. And the gamma delta T cell is a really powerful cell that sits at the nexus of the immune system. So it actually has properties of both the innate and the adaptive. It can kill directly, similar to an NK cell, but it can also antigen present and drive deeper immune responses like the adaptive immune system. Importantly, it can actually go from donor to recipient. It's completely MHC independent without any genetic modifications. And what we know now, this graph in the middle is actually the result of Dr. Lamb's work on those 6 patients that led him to do a long-term retrospective analysis of survival post-haplotransplant. In the middle there, what he's showing you is that high levels of gamma delta T cells correlate to better survival, whereas low levels, and this is naturally reconstituting gamma delta T cells, led to poor survival. So how do we take that and make it a therapy? And then what I'm showing you on the other side there is that in a pan-cancer analysis, gamma delta T cells are broadly correlated with better survival outcomes across oncology, as well as in solid tumors, and that's data from human colorectal cancer patients. So gamma delta T cells seem to be doing something in this system, and how can we leverage that? And one of the important components of how gamma delta T cells work is that their job is actually to recognize the difference between healthy self and sick self, whereas an NK's job is to recognize the difference between self and not self. So it does this, the gamma delta T cell, through a complex set of 8 to 10 receptors that actually sense cellular stress, NKG2D, membrane stress, everything you would see on a rapidly dividing or stressed cell, cells that have DNA damage. And it's able to actually sense that the cells are abnormal and then actually kill them directly, and then antigen present and drive a deeper immune response. And so this is why they're so powerful at recognizing and killing cancer cells. So INB100 is our leukemia program. And what I'm showing you here is in haploidentical stem cell transplant, relapse is a huge problem. And the reason for this is that generally haplostem cell transplant patients don't have good donors, and oftentimes these patients get a reduced intensity conditioning regimen. And what that means is that they're not well enough to tolerate full conditioning. And we know that with these two components, haplotransplant and reduced intensity conditioning, we get about 50% relapse at 1 year. And these numbers have been recently confirmed by large-scale analyses looking at haplotransplant. And what I'm showing you on the other side is actually mortality. And the problem that you see here is that with these patients, when they relapse, they often die. So the goal here is how do we hold these patients in remission, because there really is very little else for them once they start relapsing, particularly in this population which tends to be older and have complex leukemias. One of the challenges of any allogeneic cell therapy is how do you evade the immune system? And so what I'm showing you here at a very high level is the challenge. So many companies with gamma delta T cells will take unmatched gamma delta T cells and put them into a recipient. And that has not been very successful. And part of the challenge there is that you're not necessarily narrowing your question. Our first question is, how do we know, or can we tell, if the gamma delta T cells are effective at holding these patients in remission and eradicating any residual leukemia? But in order to do that, we need to know that our cells are persisting in these patients. What I'm showing you here is a log scale of gamma delta T cells that were dosed in patients, and what you can see is in that green circle, when your NK cells start to come back after transplant or after any immune depletion, your NK cells will do what NK cells are going to do, and they're going to recognize something foreign and they're going to eradicate it. And so that's exactly what you see in a lot of allo cell therapies, is as soon as the NK cells come back, your allogeneic cell therapy will be eradicated. And in that graph over there, because it's log phase, even at the highest dose level, you go to almost zero. So IN8bio has decided that in order to evade the immune system in this early trial to try to determine the efficacy of gamma delta T cells, we've haplomatched, meaning that when we get a haploidentical bone marrow donor, we also take an apheresis product from that donor to manufacture our gamma delta T cells. We and others have demonstrated that simply haplomatching those gamma delta T cells is sufficient to evade the NK cells, but we needed to show this in larger scale human trials, so here we are. So we did a dose escalation. We did 1 × 10⁶ cells per kg, 3 × 10⁶, and we actually stopped there as our recommended phase 2 dose, and I'll explain why. What we were looking at here was safety, MTD, DLTs, and importantly, could we actually hold these patients in remission, where we expect 50% to relapse at 1 year and almost 25% of them to relapse in the first 100 days. I'm showing you here why this study is proposed to work and what we observe. And the idea here is that they'll get their stem cell transplant, but we know that those high rates of relapse are due to residual leukemic cells. So we give the gamma delta T cells following the transplant, the idea being that we can eradicate those residual leukemic cells so that the patients do not relapse and we can hold them in remission. I'm showing you the patients that we have on trial at current, and the reason I'm showing you this is because we did not cherry pick our patients. We have patients with FLT3, trisomy 8, Philadelphia chromosome, P53, and many other really poor cytogenetic indicators that would indicate that they would relapse quickly. Here I'm showing you that the treatment emergent AEs were very low. We saw some grade 1-2 GVHD, which is expected, but the important part is that every single patient that we've treated using our gamma delta T cells post-haplotransplant remains in complete remission. The furthest out beyond 3 years, and we actually have 6 beyond, I believe here, 5, 6, beyond 1 year. And this is data as of November 2023. This data will be updated at IHA this year. We have started enrolling and we've announced an expansion cohort. So the initial cohort had 10 patients. At the time of IHA, all 10 patients should be approximately 1 year or beyond. So we'll be updating that. But what we see here we think is truly remarkable. They're very complex cytogenetics. These patients have an average age of late 60s, early 70s. We did not necessarily expect to see this, and we're very pleased that we do. We think it brings us full circle. So what I do want to show you here is maybe we were just lucky. And that's a question we actually get a lot, and fair enough in a small cohort. So maybe we were just lucky, and we had a bunch of people with FLT3 who just went into remission, and that's what happened. So here I'm showing you the immune recovery. And I just want to draw your attention to two things. One is the absolute NK count, which shows you that the NK cells are back. So the NK cells come back on post-transplant, and that the gamma delta T cell number does start to increase, as well as your T cells and B cells. So the immune reconstitution is happening as it should. But what we actually see when we look at absolute gamma delta T cell numbers is that at 60 days post-transplant, we actually see a 49-fold increase in patients that have gotten our dose level 2 in gamma delta T cells, as opposed to patients who've gotten no gamma delta T cells, and an 8-fold increase over cohort 1. The reason that number is important, 8-fold, is because there's only a 3-fold difference in dose level 1 to dose. Not only are we seeing expansion of the gamma delta T cells, but we're seeing this persist 5 days. And this is why we believe that we're holding these patients in remission, that residual leukemic cells are likely being eradicated over time by this expanded, persistent population of gamma delta T cells. And this is actually the first time that persistence and expansion of a gamma delta T cell or any allogeneic cell therapy has been demonstrated. So we believe our alloevasion is working, and we believe that we're seeing persistence and expansion of these cells. We're also seeing IL-15 that's upregulated immediately after our infusion of gamma delta T cells, demonstrating that there's a homeostatic reconstitution of the immune environment that's happening, and that's positive. And we're not seeing increased levels of inflammatory cytokines that would be concerning. So for all of these reasons, we've gone with dose level 2 as our recommended phase 2 dose. This is just a quote from our first patient who is now out almost, in this graph that I showed you, 3.5 years. Showing how powerful this is when really many people think that leukemia is cured with transplant, but in many patients it is not. And how do we bring this then into solid tumors, or how do we bring this and combine it with targeting so that we can more broadly apply it? And so very briefly, I'm going to touch on our CAR platform. This is unique in that we call this a non-signaling CAR, because I told you at the beginning that the gamma delta T cell has 8 to 10 receptors, and it's that complex set of receptors that dictates when it kills and when it doesn't kill when there's sick tissue in the body. And we don't want to override that system. But what we actually do instead here is we put a CAR on the cell surface that has no intracellular signaling domain. So that CAR acts just like a GPS to get the cell where it needs to go in the body. But then the cell also needs to be expressing stress signals for the gamma delta T cell receptors to engage, and then that induces killing. The CAR itself will not induce killing. And so that allows us to avoid on-target, off-tumor killing and the toxicities we've seen in so many cell therapies. So initially, we're looking at some complex AML targets as well as solid tumors that we've not disclosed yet. So CD33 and 123 are 2 targets that we know are excellent targets. We also know that they're expressed broadly on hematopoietic progenitor cells, and that leads to a lot of toxicities. Here I'm just showing you some preliminary data, and this shows you that when we use our non-signaling CAR in a CD34 progenitor population, we get very, very low killing, even with the CAR expressed on the gamma delta T cells. And actually, we get less killing with the CAR on it than we do with an untransduced gamma delta T cell. And then when we're treating cancer lines here, you can see that we do get separation of the curves, demonstrating that we can widen the therapeutic window by adding our non-signaling CAR to help direct the gamma delta T cell where to go. And that helps you avoid some of the first pass clearance in the body, get the cells where they need to go, and still have discrete killing of tumor versus healthy. So really, we've taken this 30-year journey here in about 15 minutes where we identified gamma delta T cells. We determined how to manufacture them. We actually manufacture all of our own cells for the phase 1s and phase 2. We've brought them into the clinic, and we've demonstrated that using gamma delta T cells in a way that leverages their natural capabilities allows us to keep patients in remission and hopefully steer forward in a complex cellular therapy environment. So thank you very much for your time, and I am out of time.